So welcome back students to another lecture of MTT 205 mineral beneficiation process, and for today we have efficiency of ore processing operations. So we have the module 1 introduction to mineral processing. So today the topic for discussion is this particular highlighted area, quantitative representation of mineral processing operations and its recovery, and what you mean by the terms like ratio of concentration, efficiency, and those kind of recovery and economic recovery. Those are the terms we are going to deal today. So in this particular slide, we are going into beneficiation operation and its basic concepts, suppression concepts, and we have the table here. So it is clearly mentioned here what is the beneficiation of operations we are doing and the basics of suppressions. So here it is shown what are the factors, or otherwise what is the basics of suppression process helping us for this beneficiation operation. For example, for the first example, hand sorting. By the function of color and the texture, we are sorting out the particle from the gang material. So we are enhancing that particular function, and we have some other processes also, like the mechanical sorting, where we rely on friction and its shape. We have gravity suppression, and we are using the factor like specific gravity or size, and we have flotation wettability, same specific gravity. And magnetic suppression means we are using magnet in order to separate out the valuable as well as the gong material, and we are helping with the help of magnetic susceptibility, we are enabled to separate out the gang and the valuable minerals. So these are the beneficiation operation and the basics of the suppression. So we have a terms like concentrate and the tailing. So what do you mean by concentrate? That is the valuable mineral, whereas the tailing is the base product obtained from beneficiation operation. So these are the general terms in which we separate out minerals in a beneficiation plant. So in the previous slide, we already mentioned what do you mean by tailing as well as concentrate. But we have an intermediate state called middling, that is the valuable mineral particles that are not completely liberated during the size reduction operation. There are some particles in between. So some particles are termed to be as middlings, and this contains both the valuable as well as the gang material. So such particle can be separated by the mineral beneficiation operation. This is a furthermore third operation, or the third process. We term this process to be as middlings. So moving on, we have certain expression used in evaluation of beneficiation operations. So it is denoted in this particular table, whereas the F, C, T are the terms and we are using as a normal expressions, and we have the explanation here. For example, F is termed to be as the weight of the feed, and C is denoted as the weight of the concentrate, and T is the tailing. And we already discussed what we mean by feed and concentrate and a tailing. Feed means the initial material you are feeding, the initial product, and the concentrate is the valuable as well as tailing is the unwanted product. And we have further classification, further expressions like F, which is termed to be as the fraction of metal present in the feed, that is the material that present in the feed, whereas C is the small letter C is the fraction of material present in the concentrate, and we have the small letter T for the fraction of metal present in the tail. So from these expressions, we can finalize what is the total material used. That is F is equal to C plus T. That is the C means the weight of the concentrate, and capital T is the weight of the tailing. So this is the basic equations we obtain from these expressions, like F is equal to C plus T. That is the total material input is equal to total material output. So combination of C plus T is the total material output. Similarly, if you go for the material balance for the valuable metals they contain, we can find the expressions to be as FF is equal to CC plus TT. Make sure that both the capital F and the small letter is different in terms of their expressions, like the small letter is the fraction of metal present in the feed. So by that equation we can find out what is the valuable metal present in that particular input equal to the valuable metal present in that output. So these are the general expression used in mineral beneficiation operation. From the previous expressions, we have furthermore definitions commonly used in mineral beneficiation operations, that are the ratio of concentrate. But normally what you mean by ratio of concentration is that It is defined as the ratio of weight of the ore to the weight of the concentrate produced. So that this is the expression written here. Ratio of concentrate is F by C. So in the previous slide, we already mentioned what is capital F and capital C. So it is the ratio of the weight of the feed divided by the weight of the concentrate, and we ended up in the result of ratio of concentrate. And if you consider the fraction, we can change this particular equation into this particular equation. Both the equations are term same, but here we are taking expressions like C and D, that is the fraction, how much fraction that is present in particular feed as well as the concentrate. So we can change this particular F by C equation into C minus D by F minus D. What do you mean by C minus D? C is nothing but the small letter c, that is the fraction of metal present in the concentrate, minus its tailing, that is the small letter t, divided by the weight of the fraction of metal present in the feed divided by minus its tailing. So I hope the expression is clear. It is almost similar with the ratio of concentration written in the previous example, this particular equation. So we have F and C here. So definitely F will be more in number, like the fraction will be, feed will be definitely higher than that of the C, that is the concentrate. So the value of F is more compared to C. That means the value we obtain from the ratio of concentration will be that the denominator is lesser than that of the numerator. So that means we have a ratio of concentration in a higher value. And next we have the ratio of recovery. Here the term will be totally reversible, like the ratio of concentration. Here you can see the ratio of recovery will be Cc by Ff. That means it is defined as the fraction of total amount of valuable metals or minerals or materials present originally present in the ore. Imagine you have the feed and we have the concentrate, and what how much is the valuable mineral present in that particular concentrate, we have to find that. So that is termed to be as the ratio of recovery. How much, what is the recovery, what is the ratio of recovery means, it's nothing but it's a ratio of Cc by Ff. So C is the concentrate and F is the feed, and here the feed comes in the denominator, and C is in the numerator, and we have its fractions multiplied along with both the terms, and we have the ratio of recovery, the same time eliminating the value of T, that is the tailing. If you eliminate, if you reduce tailing with our feedings equation, we ended up in the terms of assay value. Assay value means the valuable mineral present in that particular, or that is termed to be as the ratio of recovery. Make sure that whenever a term T comes, that is termed to be as the assay value, we are finding the assay value formula, and these are the general terms in terms of ratio of concentration as well as ratio of recovery. And we have another term called ratio of enrichment, and it is defined as the ratio of assay value of the concentrate to that of the ore. So this is a normal definition like C by F. C by F, that what is meant by C by F? C is nothing but it's a fraction of metal present in the concentrate divided by the fraction of metal present in the feed. So these are the three basic terms used in mineral beneficiation operation. So moving on, we have the next topic called economic recovery. And this term, what do you mean by this particular term, economic recovery? The recovery is the percentage of total metal contained in the ore that is recovered in the concentrate. So what is the total amount of metal that is obtained, or other words recovered in the concentrate? We have the terms called tailing, concentrate as well as feed. So what is the valuable element, otherwise the valuable metal obtained, otherwise recovered in this particular concentrate is termed to be as the recovery. So next we have a curve here, that is the recovery and the grade of concentrate. We, from this graph it is evident that how the curve will be forming for recovery and the grade of concentrate. Grade of concentrate means what is the valuable mineral present in that particular concentrate and its amount, that is the grade. And from this particular graph we can take an example for the explanation. Imagine you have a gold ore, and the rate of recovery will be very less, for example, whereas for the grade, the high grade or for the gold, that will be the curve will be present here. So if you want to get the high grade of gold ore, the recovery rate will be extremely less. whereas the low grade can be easily recovered. So I hope from this particular curve, it is clearly evident how the process will be, how the process of recovery is possible. So it is the duty of the mineral processor challenge to move the whole curve to the higher point so that both grade and recovery are maximum. In this particular area, where my mouse pointer is right now, this particular area is the optimum area in which the recovery, both the grade as well as the recovery rate, will be maximized. So this is the area we are more dealing with. Otherwise, we are more interested in this particular area as a mineral processor. And the main objective of studying this mineral beneficiation operation is that the purpose of mineral processing is to increase the economic value of the ore. We want to increase the value of the particular ore. That's why we are doing uh, certain process in order to increase the economic value of the ore we are getting. And the importance of recovery grade relationship is determining the most economic combination of recovery and grades, which will produce the greatest financial return per ton of the ore treated in the plant. So this is a major objective of as a mineral processing engineer. We have to make sure that the economic value of the ore is very high in terms of their recovery rate. From this graph and from this explanation, I hope you understand what you mean by economic recovery. Next, we have another perspective for economic recovery and its efficiency. So it is the ratio of the actual value of the concentrate obtained from a ton of ore to the value of the concentrate theoretically obtained in the mineralogical pure form from a ton of ore. So what this means is that, for example, whenever you go for an ore processing operations, there will be an expectation after theoretical means we are expecting something that we can term to be as that our expectation. This much ore will be extracted from this ore. This many mineral will be economically we will be going to extract. So that is our intuition. Otherwise, other theoretical knowledge from the calculation point of view or some other means, we are obtaining some theoretically, we are expecting this much or we can economically obtain. But what is the actually what we are getting after all the process? That is termed to be as the actual value of the concentrate. So it is a ratio of, in other terms, we can term to be as the reality divided by what we expected. So that is termed to be as the economic recovery. So we have an example here. If 0.20 ton of lead concentrate worth 10,000 per ton is obtained in the practice from an ore that theoretically should yield 0.18 ton of mineralogical pure galena. What is shown here is that theoretically we are obtaining like 1.18 ton should be produced, uh, uh, pure galena should be produced from this concentrate. So that is our expectation. But reality what we got is zero point 0.2 ton of lead concentrate worth 10,000. So that is the comparison. This is expectation and this is a reality. So from the explanation, we have the final equation: economic recovery is equal to zero point 0.2 ton of lead concentrate into its cost, that is 10,000 rupees per ton, and that is our the reality what we got from our ore process operation. And this is the expectation, what is that: 0.18 ton of mineral ore into the amount of the cost for this particular extraction, and ultimately we are getting 74.1 percentage total economic recovery rate. So compared to that, we have a high economic recovery rate. So we got a high recovery rate, and in order to achieve furthermore, or in other words, to achieve the recovery to its maximal possible extent, the ore is repeatedly treated using another unit of same devices, or some other operations can be incorporated in order to maximize the extraction process. And with this is my reference used for preparation of this particular slide. So with that, I am ending today's lecture. I hope to see you guys for the next lecture. Thank you.